So far, we have treated the degree distribution of the network as the most important factor in how resilient the network is going to be. But we've paid no attention to how those nodes are actually wired together. And one simple way of capturing who is wired to whom is to look at assortativity, specifically degree assortativity. In general, assortativity could just mean whether like nodes associate with like. When we're talking about degree assortativity, we're looking at whether nodes who are social, have lots of connections, are connected to other nodes who are likewise social, or is it the reverse? Is it that the hubs are associated with the hermits, the people who have very few connections? And if we look at different kinds of networks, here's an example of an assortative network where you have the hubs connecting to other hubs and the low degree nodes connecting to other low degree nodes. Here perhaps this topology is random. It reminds you of when we grew a preferential attachment network. And here the network is disassortative. So the hubs like the low degree nodes, and yeah, that basically captures it. There are different ways in which you can capture this. So one is to actually enumerate all possible pairings of degrees across the edges and look at the same property in a randomized network to see, and the reason why I randomize is just to see, sometimes at random you'll have a high degree node connecting to a low degree node. So if you were to do this for the internet, here's what you would see. You would see that these medium hubs, and having 30 connections is not that medium, tend to be connected with relatively low degree nodes, and the low degree nodes actually end up being connected with even the highest hubs, versus the highest hubs tend to be connected either with low degree nodes or with other, very high degree hubs. So it gives you a more rich representation of who is connecting to whom. You can simplify this, right? This was a 2D histogram in essence, almost a 3D plot, right? The coloring was the third dimension. We can reduce this to a 2D plot if we look at the degree of the node and then look at the average degree of the neighbors. And in fact, it gives you extra sensitivity. Do you remember how I said you can test your models by doing additional measurements? Well, here's an additional measurement that, in fact, the regular Barabashi-Albert preferential attachment model, it fails. It has no trend in the average degree of the neighbor as a function of the degree of the node. But if we look at the physical internet, it says that the average degree of the neighbor falls the higher the degree of the node. And so it wasn't until the fitness model, which came just a year later, within a year, where the probability that a node gets one of those new edges associated with a new node, it depends not just on the degree of the node, but also its inherent fitness, that you get this kind of relationship which is much closer to what you observe in real life. And there's I don't know if you can hear the crow, but it wants to chime in on this presentation as well. And then to simplify even more, you can just look at a single number, which is over all the edges, you just take the correlation between the degrees of the nodes on either side. So for example, for the internet, you get this slight disassortativity of minus 0.2. And of course, you do lose some information. For example, yes, on average, the network is disassortative, but we also saw that for the highest degree nodes, they were actually likely to both be connected to each other and to the very low degree nodes, and it was the middle that was the missing chunk. Still, it's nice to just be able to characterize this property with a single number. So if you'd like a single number, then you can just look at this correlation. I mentioned that you can talk about assortative mixing more generally. So if you were talking about social ties, you may be looking at race and income and gender and age. You can look at food webs, herbivores and carnivores. I'm assuming in the food web, it might be a bit disassortative there. Um, and we already discussed the internet in terms of the degree, but maybe really what is um, the property that they're really connecting on is the type of node that they are, whether they're high-level connectivity providers, internet service providers, or consumers. And in general, when you're talking about social networks, you talk about homophily. The term birds of a feather flock together is saying exactly this, that individuals in some scenarios will tend to associate on observable characteristics, for example, age and gender. To check our understanding, will a network with positive or negative degree assortativity be more resilient to attack? And for this, let's go to NetLogo. And what I'm going to do is I'm going to set up a topology, and this network is going to be disassortative. That is, the high degree nodes are going to be connected to the low degree nodes. And the way that I did this was by taking the originally grown network and then rewiring. And the rewiring is accepted if it, in this case, decreases assortativity and not accepted otherwise. So let's try and attack this. And the way that we're going to attack it is we're going to select the 10 highest degree nodes, and we observe what happens to the network. Now let's grow an assortative network. And you should see the high degree nodes clumping together and the low degree nodes being pushed out to the periphery. And hopefully it will finish rewiring soon. But definitely you see this dense central core. Now we're going to attack, and we can observe what happens. And here the red nodes are in the giant component. So going back to our presentation, hopefully what you saw was that in the case of assortative mixing, there was very little impact. We disconnected these parts of the network, but in general, there was so much redundancy in that central core that we didn't actually end up breaking up the network. In the disassortative case, however, a lot of these nodes were connected just to the hubs, and so once the hubs were removed, the network was pretty much broken up with the removal of just 10 nodes.